God, please. Alrighty, let's get started. Hello everyone. So my name is Amandeep Kaur and I'll be presenting my course project for CS 886 today on the title Beyond Single Dimensions with Explainable AI, Investigating the Challenges Hindering the Explainable Artificial Intelligence Implementation in the Multi-modal Medical Domain. So let's get started. I'll start with the table of contents. Firstly, I'll start with introduction, wherein I'll describe the problem statement. Then I'll move to the research questions. So I'm discussing 3 research questions that I'm proposing in this project. Finally, I'll be talking about the methodology. I'll discuss the methods, how I'm answering these 3 research questions. I'll talk about the progress done so far, describing what all checklist I have already done, what all things are still in progress. And then I'll also be talking about SWOT analysis, where I'll be discussing the strengths, the weaknesses, and the future work in this project. Finally, concluding the presentation. So let's get started with our introduction. So as you know, with advancements in computation and medical data availability, the field of AI has huge potential for healthcare industry. But even if you go to the hospital today, you will visit a doctor, not a machine. Which brings us back to the question, why hasn't the healthcare industry embraced active deployment of AI? And the reasons are many, right? So I have listed only 6 reasons. The first one is trust and reliability concern. You would rather trust a doctor than a machine. Secondly, AI's black box effect. Researchers themselves do not know how the algorithm is building up on the predictions that it does, right? Then the third point is lack of transparency. You are not sure why the model predicted what it predicted, right? Then you also have multimodal data integration challenges. This is an interesting one. If you look at a doctor has over years of experience, right? And then they can like integrate MRI data, medical reports data together and form a conclusion. But this is a challenge for technical aspects or from the computation point of view. Then we have resistance to change. We rarely want to change our methodology, right? And then lack of accountability. Who is accountable when anything goes wrong? So these are some challenges. And in this project, I try to answer and base my foundations on the 3 bold challenges that are there in the industry right now. So let's get started with the research questions that I propose. Now, there are 3 research questions I'm proposing. The first one is probing challenges in medical explainable AI. So herein I'll talk about what are the challenges that are impeding or hindering the effective implementation of explainable AI within the medical field. This is something that I do with the use of case studies. The second one is enhancing insights, integrating diverse medical data. Now, this is something which is like based on how do you evaluate the effectiveness of integrating multiple data sets as compared to just a one single medical data source. This is also something I'll be doing and proving my point using case studies. The third one is integration of explainable AI, initial versus post hoc. Now, here I'll be contrasting the integration of XAI algorithms when you're designing versus post hoc implementation. And herein I propose an architecture which combines RQ1 and RQ2 together with the name WhatNet Fuse. Next, talk about the methodology for answering research question 1. Now, medical data sets have different modalities and have to be interpreted cautiously, right? Because the reason is you are dealing with a person's life. The traditional black box models are not at all transparent, and explainable algorithms were trained on real world data sets like ImageNet. And that is the reason why, when you're answering research question 1, I conducted a case studies on 9 most popular explainable AI algorithms on medical image and text data. In the present slides, I'll be just highlighting the fallbacks for 4 algorithms: Lasso versus Shapley for text data and Lime versus GradCam for image data. Before moving forward, we need to understand some technical concepts. How are these algorithms, XI algorithms, categorized, right? The first one is through dimension reduction, which is like using lasso and cluster analysis. In dimension reduction, basically what you do is like you have so many features. You find what all features are like correlated, and then you can try to loosen or basically not include some features, right? So you're basically reducing the dimensions for your data. The second one is feature importance. Feature importance means like you have so many features. Which of the features are so important for your model's prediction? So you choose that. And that can be done using Shapley values or deep left, right? Then thirdly, we talk about attention mechanism. These models are something which are based on like the model pays specific attention to a certain, say, if you're talking about an image, a certain region in the image, right? Which is something uh, which is like used by GradCam or superpixel maps, right? Then we move to the surrogate representation, which is LIME and LRP, wherein instead of focusing on global analysis, you just focus on local analysis and find local interpretable models. Finally, we talk about knowledge distillation and rule extraction, which is like Bayesian. And this is more related to if and else statements and also probabilities. So now that we have an idea about these concepts, we can now move forward about the 4 case studies that I'll talk about in this tutorial, in this lecture. And then what all concepts I really want to, kind of bring about in this topic. So the first one I chose is lasso regression. Lasso regression comes from the XAI via dimension reduction, wherein what happens is that lasso assumes linear relationships with the target variable, and it will just choose one of the highly correlated variables or features, right? For the task of textual medical data, I chose this data set from heart rate risk prediction, wherein you have like 27, around 24, 27 features which are responsible for the data. And the final prediction is heart rate prediction, heart risk prediction, which is like whether the person will get a heart risk, kind of heart attack or not, right? Which is like a 0 1 label, right? So I basically ran the lasso regression model, and what I found out was that from the feature importance plot that I have plotted here, there were 3 variables, basically features which were very much important, which is BP systolic, cholesterol, and triglycerides. From a layman's point of view, I think these are very important, and it's a great plot, right? But what is the fallback for these algorithms? The fallback is that if you think about it's a heart risk prediction data set. It's so don't you think like heart rate should come more, like it should be more focused, or any kind of previous heart rate problems should also be taken into account? Age should also be a matter of fact, right? And these are some questions which I had in mind, but that's what the lasso is all about. It will choose one of the highly correlated features, and this is the fallback that is like that can be a restriction, because the possibility of losing crucial features, which will be still relevant for clinical predictions on a case by case basis, can be common. And these are like important features which can be neglected, and hence can be detrimental for a patient, right? So that is the reason this algorithm fallbacks. Let's now talk about Shapley values. Now, Shapley values are basically from the feature importance point of view, and they are calculated in the context of like a game theory, right? So, 2 players, which all features are like better for the prediction and things like that. I plotted the mean Sharp values and average impact on the final prediction here. And interestingly, you see that age comes out as a very important factor, followed by triglycerides and BP diastolic. Just to make you sure, in the previous one, it was BP systolic, cholesterol, and triglycerides. Herein, Shapley says that age, triglycerides, and BP diastolic are important. So, first, let's talk about the Shapley values. Now, these values are very model specific, and from a layman point of view, I think these definitely make a good, feature important value. But these might not be like very transferable. So Shapley values are very model specific. I use cat boot classifier for this classification point, right? It could be the results could differ if I choose another classifier. And interpreting the working of the algorithm might be a challenge for non-experts if we talk about the Shapley values. But I would like to give my insights also on this problem statement, right? I feel like what is happening whenever you go to a doctor, the doctor is going to see your features, I mean your ailments, and going to say only one thing. So regardless of whatever algorithm you're using, I believe that the final prediction should be the same. While Lasso and Shapley values are having different mathematical structuring of working and things like that, but their final feature importance values or feature importance variables should be more or less, kind of same. Because if you see the Lasso, the age is not at all herein. The BP diastolic is not at all herein, while in Shapley, you see age and BP diastolic are coming in the, kind of the top criteria, which makes me feel that these algorithms fail when it comes to like interpreting. How will the doctor choose if you just give these two algorithms and these two predictions to the doctor? How is the doctor going to decide whether this one was the better one or the second one is the better one? So I think herein is a need for more explainable AI algorithms specifically designed for medical data sets. Let's now talk about image data set. This is an image that I took from a paper here, and I have mentioned it's from Meta. It's a metastatic liver cancer, the 25 mm diameter. And you can see here that I've used Lime, and what Lime does is like it's like approximate the behavior of a black box model with local interpretable models, right? So instead of focusing on the global aspect, it focuses on a local aspect. And you see that Lime failed to even detect the tumor in this image, and instead it basically the top predictions were breastplate, cuirass, pitcher, cleaver, and hatchet, which makes me feel that these algorithms cannot be used in the medical domain just like that, because this is a huge tumor. Even if a layman person like me, who's not even expert in this domain, can find out that okay, this is something which is absurd, which is not normal, a model, a explainable model should be able to find it, right? Which brings us to the fallback that this is limited to the align is limited to the input features, and it also lacks like the clinical or the medical context, which makes it like not usable in the domain. Let's talk about GradCam. GradCam is like a better version, I would say, of explainable AI. And I was at least relieved to see that at least it was able to highlight some areas. Not 100% true, but at least some areas. Um, One thing I like to notice or take into account here is that, model predictions, when you talk about these models were trained on ImageNet data, right? ImageNet data, which is like data of normal things, right? And that's why the predictions are somewhat from the normal criterias like backpack, ping pong ball, right? But one thing to mention here is that GradCam, how it works is like it will just highlight the important regions which have like led to the final prediction of black backpack or black swan, right? But the fallback of this algorithm is also that these algorithms do not advise on what makes the region important, what is there in the region, why it's important. And this can be so much frustrating for the end user, especially when they do not know the rationale why this region is important. I gave you the context, right? That okay, this is something which is like having a tumor. That's why you were able to make out that okay, this is something which is like important region, right? But it might not be the case every time, so you need to give rational in the attention mechanism modules. Now let's delve deeper into the research question 2, which is enhancing insights, integrating diverse medical data. Now, the expectation in machine learning is that data fusion efforts will result in an improvement in predictive power. And this has been proven by a review by Huang et al., wherein they basically found out that multimodality fusion models actually led to an increased accuracy of like 1.2 to 27.7% over traditional single modality tasks. And for answering research question 2, I discuss on 10 multimodal medical studies which have proved this concept. And in the slides, I'll be just highlighting 2 such studies, right? So let's get started with the case study one by Karazami et al. Uh, these authors basically worked on the dermatology clinical domain, and their fusion details were like they use CNN extracted features. The medical images that were input were the dermoscopic images, and the text records were patient data, as you can see the columns, right? And the number of samples were 1191, and you can see from the data that from the model performance that they had a good accuracy increase from 6.4% to 15.5%, as compared to the standalone models, which proves the point that multimodal data is actually beneficial for accuracy increase. Another case study that I will show is case study by Ni et al. And they basically worked in the radiology oncology in clinical domain with using same CNN feature extractions. And the input image was that of MRI images, right? The text records were patient data. You can see the number of samples is definitely low, but the model performance is great. For MRI fusion and MRI, the comparison, it was 9.62% increase, while for fusion and demographics and tumor features, there was a 27.7% increase, which is a huge increase, which proves the point that multimodal data sets, especially in the domain of medical images, medical field, can be really, kind of useful in the domain. Which brings us to the research question 3, which is integration of XAI in multimodal datasets, initial versus post hoc implementation. So I discussed RQ1, which proposes the need to improve and deploy explainable algorithms, while RQ2 discusses the efficiency increase by using these multimodal data sets, right? Now, the need is to combine RQ1 and RQ2 and propose an architecture that is both explainable and can handle multimodal data sets as well. So answering RQ3, I proposed the architecture of WhatNet Fuse, a multimodal explainable AI architecture for medical domain. In the slides, I'll be discussing the architectural design for WhatNet Fuse, and implementation would be a future task because given the time constraints, right? So before moving forward, I would like to just talk about 3 technical concepts. How do you fuse the data, right, into a model? So there are 3 methods to do this. The first one and the most popular one is early fusion. Early fusion means that you basically do fusion at the feature level. So you're joining multiple input modalities, converting them into single vector, and then passing it to the model. The second is joint fusion, wherein you're basically learning the feature representations from immediate layers of neural networks, and then and then you are basically propagating the loss back to the model, and then this is like an ongoing process. The late fusion is wherein you're leveraging the predictions from multiple models to make a final prediction. This can be done using averaging or majority voting. Finally, I propose the architecture for WhatNet Fuse, which is a multi-model explainable architecture for medical domains. If you talk about conceptually, there are 4 inputs that can be fed into the system. The first one is speech data. The second one is textual data. The third is imaging data. And the fourth is video data. Technically, speech data can be converted by using a Python library speech recognition to textual data. Right. And video data can be converted into frames, can be converted into image data again. So technically we have 2 data sets, data streams, textual and imaging, right? Which is like multimodal data for sure. For textual data, we can again have genome data, EHR data, and doctor's note. For imaging, we can have different modalities like T1, T2, FLAIR, which is something I explained earlier as well, right? And how do you move forward with this? It's basically, so let's talk about the text part first. So the text part, you will have this data multimodal data, you will convert it, you will reduce the dimensions using PCA and then vectorize it. And herein, you put in the concept of Shapley values. So you're basically assigning feature importances to the to the model, to the vectors, and then these vectors will be then fed into a vector aggregator. From this point of view, you can say that we are trying to, so this point of view is something of early fusion, wherein we are inputting multimodal data, but at the same time, we're also explaining or basically giving a feature importance to the vector. So by implementing the Shapley values, right? And let's now talk about, so this text part is one part that's done. The second part is that of imaging data. And imaging data, you can have different modalities, T1, T2, FLAIR. These are like different point of views. T1 can be something for tissues, T2 can be something for tumor detection and things like that, right? And herein is a concept that I use from my previous work, citing grad excepunet, which is a model, which is also a fusion model that I made in my undergrad. And therein, I use the concept of explainability fusing into the model, which is like something we call joint fusion, right? So the concept or the idea is that one part of the data is the imaging data, and the second image data, the same images, would also be fed to an explainable algorithm. It could be, for example, a GradCam saliency map, for example, and this data will also be given to the feature for feature extractions. And the concept here to notice, and it has been a proven fact before also, that prior valid knowledge will that is coming from GradCam will act like a way to minimize the search for optimal parameters. This is a study by Diligenti et al., which have proved this point, and that is a concept that I'm using in the imaging data. And then I can convert that into vector aggregator, and then there are three tasks that can be performed. The first one is using UNIT, which can be like medical image segmentation. The second would be LSTM, wherein you basically generate your reports, right? And the third is CNN prediction classification normal task. So this is the architecture of WhatNet Fuse. And I would like to say that I use early fusion in this data. I use joint fusion in this part, and then late fusion in this part. So I'm using all the fusion aspects in one algorithm. Progress done so far, I have done case studies on RQ1, RQ2 are completed. The conceptualization of architecture of WhatNet Fuse is done, and report writing is in progress. I'll talk about the SWOT analysis now. The strength of the study is like it's a comprehensive study done on existing most popular explainable AI algorithms in the context of medical domain while using medical data. The fusion of RQ1 and RQ2 conceptualized as RQ3, which I think is a novel thing. I also propose a new architecture for fusion of multimodal data sets with explainable AI. The weakness is that this is a concept which is not peer review, and the domain expert analysis is still missing. The case studies done definitely are limited and cannot be generalized, but they are just a point of view to proving the point that we still need more advancements in this field. The opportunities are many. There's huge potential for innovating explainable AI algorithms specific to medical domain. Then implementation of WhatNet Fuse with real-world medical data is one of the future aspects I'm thinking of. And another ambitious topic could be a deployable UI application for the model, which would be a great advantage to doctors, right? The threats are that time constraints for implementation is definitely an important aspect. I'm also in my master's degree, completing my other projects and research and everything. It's too much for a time. It's too much for times, right? And secondly, implementation in real world as a deployable architecture is still questionable because, as I told you, you expect a doctor, not a machine. When you go to the hospital. So the deployment would be a task, and that's kind of questionable, right? Finally, the conclusion, what you learned from this presentation is that XAI, explainable AI for healthcare, is the need of the hour. Present explainable algorithms lack transferability to medical domain. The introduction of multimodal dataset for medicine can be utilized with AI. An approach was discussed for fusing explainable AI and multimodal medical dataset, and the future aspect would be to deploy this architecture. And with that, I thank you all for listening to this presentation. I also give credits to SlidesGo for their presentation template that I used. And that's it from my side, leaving you with this SWOT analysis.